All right, okay, so welcome back, everyone. I'm happy to also introduce now Nadav Dym, who is going to talk about mapping multisets to vectors. Before we get started, just a very quick announcement. So in the last hour, we would like to have a bit more of a discussion and kind of a wrap-up. So we have some identified some volunteers who will speak for a few minutes, for instance, saying something that they learned about in the workshop, what they found interesting, what are interesting research problems. And also I had, my talk that starts in an hour from now will also be shortened so that we have more time also for this discussion. And I will also go more towards this. So please, stay here and also maybe think about some questions, some comments. We really want to also include audience members into this. So please go ahead.
Okay, thanks. So I'll start. First of all, mention my collaborators. So Tal and Snir and Jonathan from my group. Yair, who's former from my group, and Stephen Gortler. Okay, and the topic I'm going to talk about is functions on multisets. So I assume many are familiar, but so a multiset is a collection of unordered elements, and we want to map multisets to vectors, like we'll talk about soon. This is something which is done routinely inside graph neural networks. So the input is a multiset, and so the only difference from a set is that you can have multiplicities, right? The output is a vector. And we want to talk about functions on multisets, which also, functions mapping multisets to vectors, which also sometimes are called permutation invariant functions. These are basically identical notions. Okay, and in a nutshell, what we're going to be talking about is two questions. One is how to make such functions injective, so a mapping from multisets to vectors, which is one-to-one. The second question is sort of a more refined notion of injectivity called Bi-Lipschitzness. You want to preserve distances. And what we'll show is that in an appropriate sense, multiset functions that are based on sorting are better in the sense of these two questions than sum or mean or max aggregation. And we'll show some experiments related to that. Okay, so that's the plan. Okay, and we'll start with sort of some classical results from 2016 and so, which were probably mentioned to a certain extent already. Okay, so first of all, message passing neural networks. So that certainly was mentioned, right? So we have the standard thing, right? And what, in our context, what's important to note, right? We start with the node features, and then we have permutation invariant functions, multiset functions, where we aggregate over the neighbors. We do this iteratively. We have the combine function, which just maps a pair of vectors to vectors. And after we do this enough times, then at the end, we also have some sort of readout step, where we aggregate over all nodes in the graph. And again, each one of these functions basically maps a multiset to vectors, right? So that's why we're interested in these things. And in particular, we have these results that message passing neural networks cannot separate graphs that are not separated by 1WL. But on the other hand, message passing neural networks, which are sort of sufficiently expressive or maximally expressive, are equivalent to WL. And that's related to get this, you need all of the functions along the way to be injective. Okay? Or at least that's a sufficient condition. So that's, in a way, I guess, the motivation to why we're interested in this question. Okay, so this is our first question, injectivity of multiset functions. The functions we'll be interested in often are parametric functions, so we want them to be injective in the sense that there exists some parameter, or they'll be with high probability on the parameter space, the function will be injective. Okay, and to discuss injectivity formally, we'll have to have some sort of assumptions in the domain. So we're going to be talking about multisets with bounded amount of elements, bounded by n. It should be capital N to be consistent with my notation later on. And they come from some alphabet, which is some subset of RD. Okay, and so this could be continuous or countable or finite. So usually in the sort of graph, if you want to get some sort of result on graph neural networks, then this little n would sort of correspond to the maximal amount of nodes in the graph, and sigma would correspond to maybe to the initial alphabet. So let's say you have 1-hot encodings or something like that. So that's like some sort of finite encoding. So if the features are finite, it will be finite. If the features are continuous, it could be continuous. Okay? So that's maybe our first motivation. Another motivation, which we'll discuss less about, is that you can also use injective multiset functions to approximate all functions on multisets. So if f theta is some injective multiset function, then the composition of MLPs with f theta can approximate all multiset functions. Okay, so that's that.
Also only restricted to sigma.
Excuse me?
Like the universality is with respect to that sigma.
The theta, you mean?
Yeah, not like the universality approximation of multisets. Are the multisets still restricted to those only?
Yeah, to that whatever domain you can prove injectivity on, and that domain. Yeah. Okay. So popular ways to aggregate or map multisets to vectors all were discussed here. So one popular, we want to talk about 3. There's sum pooling, where you take some f theta as some MLP, some neural network, and you apply it to all the points and you sum, right? So that's permutation invariant, does not depend on the order. There's mean pooling, there's max pooling. Okay, all these things have been discussed. Let's say in Soledad's talk and in many other talks. Okay, and sort of one of these classical results is that in terms of the question we're discussing, so sum pooling is better than the other types. Okay, so so this is a paper from Stephanie's sort of well-known paper, picture from Stephanie's well-known paper, right? So what it shows is that if you look at say you look at these two multisets, right? Where one has 6 elements and one has 3. So something based on summation, right, where you apply some function and then sum, will be able to separate these two things, but taking the mean will not be able to, because the mean basically thinks of the multisets as a distribution. So as long as the blue and red are distributed evenly, it will not be able to separate that. Okay, so in our context, this is bad. Maybe in other contexts we were discussed here, like you want to take the limit and graphons, etc. So actually, that maybe would be considered good, but today that's not good. And then there's even sort of if you take the maximum, so you can't. In general, you can differentiate even less, right? So if you have so the maximum of a multiset with this, if you have 6 elements which are the same and they're maximal or 1, there's no way to tell the difference between them. Okay, so so we're gonna basically stick with sum pooling from now on, because that's where we have a potential to be injective, right? And basically there are known results which show that at least when the domain is countable, multiset functions are injective. Okay, so you have. Okay, so our assumptions are that you have at most n elements. Maybe you don't even need this. It could be like any finite number of elements. And they come from some countable alphabet. So say maybe 1 to n or all the integers or something like that. And then in this setting, so you can, for some appropriate f theta, you can get an injective function. Okay, and as a result, this leads to maximally expressive message passing neural networks. And I put here 3 references to this result. I don't want to go into the nuances too much of what exactly each result proves. Okay, but sort of in high level, this is something we know. And what I want to talk about more now is moving from discrete to continuous features. Okay, so say we assume that all our multiset elements are coming from not from a countable set, but from all of Rd. Okay, so we have continuous features like particle coordinates in R3 or anything else. Okay, and we want to be injective in this setting. Okay, so this is also something that people know how to handle to a certain extent. Okay, and the standard thing that people usually use for theoretical results is the fact that if you take so if f is a mapping that maps each xi to like all the monomials up to degree d, up to degree n, where n is the maximal number of elements in the multiset, then you sum over all that, and that is known to be injective. Okay, so So that's a known result. It's been used in, let's say, in Hagai's paper and in many other papers. The problem, so two problems with this. So one is, which we would like to fix. So one is that f is not a neural network. Okay, so this is some sort of polynomial function, which is not exactly what people use. Okay, so the standard way to address this is that the argument is that maybe if f is a polynomial, it can be approximated by a neural network, which is true, but then you have even less control on the size of the neural network. And the second problem is that f itself, the output dimension of f is very large. It's sort of exponential in n and d. Okay, so we want to address both of these problems. So we want to get injectivity where this f is actually a neural network, not a polynomial or anything like that. And we want this to have some reasonable complexity, linear and polynomial, say, in n and d. Okay, so that's our goal. And basically now we're leaving so starting to talk about our results in our group. The first sort of, I would say it's between a result and a relatively trivial, is that if you want to get some sort of injectivity with a neural network, so this network can be a ReLU network. Okay, so here's a simple ReLU network, right? But even if it was more complicated, the picture would be similar. The thing is that if you have a ReLU network, is always piecewise linear, right? As has been discussed previously. So if you look at the domain of this function, you can break it into a finite number, maybe very big, of linear regions. And inside each linear region, right? So say inside this rectangle, the function, since the function is linear, you can exchange the sum with the ReLU. Okay? And the result, basically, inside the rectangle, the only thing that this function sees is the sum. Okay? So if I take, let's say, a multiset, which is these two purple points, I think this is purple, and then a multiset with these two blue points, and their sum is the same, then I'll get the same result, although the multisets themselves are different. Okay? So that's basically what this teaches us, is that if I take a sum over, I do sum pooling over any piecewise linear function, this will never be injective if I'm talking about continuous features. Okay? So to actually get some sort of result, we have to leave the world of piecewise linear functions and talk about functions which aren't piecewise linear. What we're going to be talking about are analytic functions. Okay? So this is for two reasons. First of all, because it's easy to prove things with them, and also because in practice, the activations that are used in the machine learning world, I think, are always either piecewise linear or analytic. I don't know. I challenge you to find a different one. Maybe there is, but I think that's pretty correct. Okay, so we're going to assume analyticity, and then we can prove the following result. So if we're looking at the space of multisets with at most n elements in Rd, and sigma is any function which is analytic but not a polynomial, then basically a simple neural network like this, right? So it's one layer applied here. You sum. This thing is injective, right? And the dimension, like the output dimension of this function, is 2 times n times d plus 1. So it's basically like the dimension of the multiset space, because you have n elements in Rd, times 2 plus 1. Okay? So that's, in a way, maybe the main result here, or one of the main results. Okay, and in a way, so this solves the problems we set up before, right? So first of all, this function f, or this function here, is a neural network, okay, which is what we wanted. Second of all, the embedding dimension is linear in n and d, and this is actually, you can show as near optimal. So for, on the one hand, there's sort of, you can show that, and showed in this second paper, that the embedding dimension is almost, as long as the function you put here, whatever it is continuous, the embedding dimension will be at least n times d. So you're at most wrong by nd plus 1, by a factor of 2, basically. On the other hand, let's say there's this paper by Yusu who reduces the embedding dimension by 1, and you probably maybe do more, but it's close to optimal. Okay, so that's that. Maybe questions up to now? Okay. One sec. Okay. The main tool I'm going to talk a little bit about how this is proven, because I think it's, well, because I will. it's called a finite witness theorem, something a theorem we invented and the terminology we invented. Okay, so the idea is there are like two steps. The first is, let's call it the infinite witnesses. And this is generally easy. So the argument here is that you want to show that if you want to check if two multisets are equal, you can do this by, sorry, I have a little delay here with the, okay, sorry, okay. So, right, so if I want to check if two multisets are equal, you can show that that is equivalent to showing that you have this equality for all A and B. Okay, so if you know that you apply this function is certainly permutation invariant, right? And if you apply this function, and okay, it is what it is, okay? So this is something which is relatively easy to prove. And if you want, it's also similar to the countable case, right? Because if you are looking at a fixed pair of multisets, then you're basically in a finite setting. In any case, so if you believe this, so what's the finite witness theorem says is that you can, given the fact that you can check whether the multisets are equal with an infinite amount of witnesses, you can actually find a finite number of witnesses for which this will be correct. And you can control the number of witnesses you need. So the number of witnesses you need is this number. Basically, it's twice the dimension plus 1. Okay, so that's the result. So this is sort of, I think, maybe the only thing here that's non-trivial. Yeah?
When you say generic, you mean up to a set of measure 0?
Yes, thanks. It's also, it's a little bit more than that. So you can, I mean, there are various kinds of generic. It's like a finite union of, maybe a countable union of manifolds of low dimension. But yeah, okay. So let me talk a little bit about the finite witness theorem itself. Okay, so this is what it looks like. So I'll try to process it. So this is the statement itself, right? If we ignore the conditions, you're saying that if you have equality for all parameters, then you have that equality for all parameters is equivalent to equality with some finite number of parameters. And this needs some assumptions, okay? So the first assumption is that the function we're talking about is analytic. Okay, so this can be relaxed, but then you need some sort of, the theorem becomes less simple. But if you want a simple with this amount of, for this statement to hold as is, you need the function to be analytic, which is why we need analytic activations. There needs some assumptions in the domain. So I wrote a countable union of affine sets, but this is mostly because that's something we understand. Okay, so certainly it's true for any vector space or a countable union of vector spaces, but it's basically true for any reasonable sets, true for semi-algebraic sets, for unions of semi-algebraic sets, sets defined by analytic inequalities and equalities. So it's not so much of a big deal. And another thing which is important is that, so we have as we said, right, if the dimension is capital D, so we need 2D plus 1 witnesses, so to speak. And this capital D you can think of as the intrinsic dimension, okay? So you have this set, whatever it is, and if its dimension is up to capital D, then you'll need only 2D plus 1. So we'll see soon where this will be helpful as an example, okay? Okay, I'll say one thing about the proof, very, very high level. Okay, so the general idea is, so first of all, I need to give credit. So I mean, the basic technique for this proof comes from phase retrieval. So in 2005, there's a pretty famous result about like how many, something similar to this, like that if you want to reconstruct a signal in C to the n up to a global phase, then you can do it with a linear number of measurements. It's 4n minus something. And basically what we do is based on that theorem technique. And we did this in 2 hops. So the first hop was we basically took this thing from phase retrieval and we generalized it to sort of a general algebraic, real algebraic statement, and so showed how you can use this to get all kinds of results related to geometric learning. And the second step, which is sort of using what's called O-minimal systems to move from algebraic to analytic. So basically in real algebraic geometry, there are all kinds of nice, if you have sets which are defined by polynomial equalities and inequalities, they have all kinds of nice results. And O-minimal systems, I guess, is a much wider field. But in particular, one of the things they're interested in is trying to find families of analytic functions which have the same properties. And this is sort of what we use. Okay, so that's it about the finite witness theorem. Okay, and so I want to go back to GNNs, talk about how this is related to GNNs, or how these results help us, right? So, and what we can get from here is, if we want to talk about MPNNs with continuous features, you can get a maximally expressive MPNN with 2nd plus 1 features per node, where n is the number of nodes in the graph, and d is the dimension of the initial dimension of the nodes. Similarly, if we go to like what Mircea was discussing before, so if we have, look at all distances and you apply something which is 2WL equivalent, so we use a provably powerful, the PPGN. Okay, so you know that this could be universal, but what you can prove is you can do it with 6n plus 1 features per node. I guess it should be per pair of nodes, which is stronger than what you could, much lower than what you would get if you used the power sum polynomials. And I think, so here is also an interesting place where this idea of intrinsic dimension is helpful, because if you think of it, right, so if you do some sort of whatever, graph neural network, message passing procedure, right, so if you start out with features of dimension 3, so maybe after the first iteration, you get to dimension 6n, but a priori it would seem like the second iteration you would get to 6n squared, etc. Like right? So every time the dimension should grow. But if you think of it intrinsically, so that's not true. So right, if you have, under whatever, at least in our setting, it's true that if you have something, the image of a nice enough function, its dimension does not grow intrinsically, and so if you look at the features after step 1, their intrinsic image is the same as in step 0, and so you can stay with a constant dimension of 6n. What else? Okay, also a result which maybe you don't really need the finite witness theorem per se for, but you can get it from there, is that if you look at, you can get maximally expressive MPNN with discrete feature graphs with a single feature per node. Okay, which sounds honestly ridiculous, and we'll soon talk about that it really is in a way ridiculous. But okay, but mathematically this is true. Okay, so as long as you're using analytic activations, you only need one feature per node to be maximally expressive.
Can I ask
Yeah.
So the universality
Sorry.
result that you have,
Uh-huh.
is it universality or separation?
Now I'm talking about separation.
Because it says universality
Uh,
of PPGN.
Right. It's also true for, so you can have 6n plus 1 features per node, and then you stick an MLP at the end.
Yeah.
The MLP can be very big, we don't know. Okay.
Can I ask you a question? So
Yeah.
For the point clouds, you mentioned this, that you don't have to increase the dimension.
Right.
But I had a similar question for the MPNNs.
Yeah, same thing, yeah.
So you don't need to, because after the first layer, you expand your dimension to 2 times n d plus 1.
Right.
All the vectors, all the n vectors now have larger feature vectors, which are then propagated, and again you have to ensure injectivity.
Right.
It
So that's
doesn't blow up.
so the point I'm saying is that the intrinsic dimension stays, it cannot grow. So if you have a mapping from, right, so initially you add, let's say n vectors, each of dimension d. And each one is now mapped. Now this whole thing is mapped to n vectors of dimension n times d, right? But if you think of it as a, so this whole thing is, at the end of the day, it's the image of what you started from, which was of dimension nd. So that the intrinsic dimension of this whole thing does not grow. Okay. Okay.
And then the second remark is, I think the last bullet is related to like a result by in Chile, I forgot the name, Cristobal. They showed also that you can actually like simulate you get like a maximally expressive MPNN using a very strange analytic function using only one dimension.
well, I know of, OK. I know of results. There was one paper that sort of highlighted this, which was a little bit after our result. And maybe they're also, maybe you send me and I'll point it. I'll find the historical context. I don't know. OK. Yeah, so send it to me. OK. And I think there are many other applications for this, which is very, I mean, this is a very useful result. But the bad news is it's only useful for us, because no one uses it except for us. So at least in terms of PR, it's not a big success to the extent that I'm actually telling you about this explicitly to try to encourage you to use this. And I would say, like, if someone publishes code, so then he's obligated to give support, right? So I promise or almost promise to give support if you have some student who's interested in, like, any type of result related to, like, how many features you need to get some sort of separation result. So send them to us and we'll help them. But I really think it's very helpful. So I recommend it. OK. Anyway, so now let's talk about whether, OK, so according to our story so far, you get the feeling that analytic activations should work better for this type of application, right? So is this true, OK? No. You can sort of see this, if all you're interested in is just seeing separation, then that you can sort of see that analytic functions do this better. Okay, so here's an example, which we did in this paper, right? So we took all the graphs from the TU data set, and there's 600 graphs, and each one of them we checked whether an MPNN with analytic or piecewise linear activation, whether it exactly has the same separation pattern as the true WL. And for, we have 3 analytic functions, and we got, 0 error here. And for piecewise linear functions, you can, occasionally you do get some errors. Okay, so let's say, at most, with a single feature with ReLU, you get 17 out of 600 errors. It's not very common, okay, but it is. You can see this difference. Here's another example, right? So if you look at this, if you look at PPGN, and you sort of do a similar thing, you look at, there's 600 graphs, you look at the error. So here we have two analytic activations and 2 piecewise linear activations, and you see that the separation is better with the green and the blue. Okay, so here you see, like, the difference, the separation gap. So you have G and G hat. What is the difference between the features? Okay, and also, but if you look at the y-axis, right? So you see that we're not doing so great. I don't know if you can, maybe it's a little small, but this is at 10 to the minus 8, this is 10 to the minus 10, okay? So I mean, again, we only have one feature here, okay? A single node per feature. So this is small, you wouldn't maybe expect to see separation, and really, I mean, this isn't real, right? It's like not, this is a very, very low separation, which probably practically has no meaning, okay? I mean, let's say if you're working with single precision, you probably won't be able to see it at all, okay? So in particular, this sort of brings us to the second question I want to talk about, which is quality of separation. Okay, so I mean, one way to try to avoid the picture we saw is to talk about Bi-Lipschitz guarantees. So this means that, okay, so if I'm going to go back to multisets now, but abstractly, if S and S prime are either multisets or graphs or something, okay. And we have some natural notion of distances between them. So we'd like to know that the features, the difference between the features is bounded from above and below by the actual distance, sort of the true set distance between the multisets or graphs, okay, something of this sort, right? Okay, so for us, again, I'm going back to multisets because that's the simpler case. Okay, so I'm going to talk about W will be the Wasserstein distance. So W squared is the minimum between basically the 2 norm of X and Y, where you're allowed to permute Y so it's as close as possible to X. I'm also moving now to the case where the multisets are of same size. I'll talk about that later, but for now they're the same size, okay? So we want to be Bi-Lipschitz, and ideally we'd like the Bi-Lipschitz distortion to be as small as possible, right? So if I have, say if the ratio between capital C and little c is 1, so up to scaling this is an isometry, that would be nice. Not so realistic. The larger it is, the worse we're doing, okay? So that's our second goal. Okay, a different way to think of this, the motivation, you can think of, say, in multiset space, we have two clusters and we have some learning problem, but it's difficult to work with. So each point like this represents a multiset abstractly, right? So maybe it's difficult to do whatever we want to do. In multiset world, we want to embed it into a vector space, but we want to preserve distances, right? So if let's say if I had an embedding that was an isometry, I wouldn't have something like this where the clustering is destroyed by the mapping. Okay, but injectivity alone does not promise me that this will not happen, right? Okay, so that's our second task. Okay, and okay, so maybe it's natural. First of all, it's remarks. So if you look at doing sum in some sort of ReLU network, so that obviously will not be Bi-Lipschitz because it's not injective. To be in Bi-Lipschitz, you have to first of all be injective. If you look at something with analytic, right, analytic activation, then it turns out that there's no way that that can be Bi-Lipschitz, although we saw that it is injective. Okay, so this is a theorem we proved. So basically, if you have a function which is differentiable at any point, and you take the sum, it might be injective, but will never be Bi-Lipschitz. Okay, and the proof of this is actually sort of the same as what we talked about before. Right, so if you think of a function which is differentiable, that means that in first order it's actually linear, right? And that means that this type of example will make it fail. Okay, so if you look at the first order approximation of this function, the first order approximation cannot tell the difference between two multisets who have the same sum, and therefore the error will only be second order. Okay, and this is sort of also part of maybe a more general result from this paper, where there's actually a more general thing here where if you have some sort of group invariant structure and you have points with non-trivial stabilizers, then differentiability always implies lack of Bi-Lipschitzness, maybe up to some trivial assumptions. Okay, so here in our case, the stabilizer is because this is the point. Right, these points converge to basically a multiset with two elements which are the same, and that has a stabilizer because you can change the order. Again, this is a general result. So okay, so that's that. So actually, if you want something which is Bi-Lipschitz, so you actually might need to be not differentiable. Okay, that's sort of the result. An interesting thing is that actually, when you look at separation, in a sense, ReLU is actually better than smooth. If you look at qualitative separation. Okay, so right, we said before that this is not injective. Nonetheless, you can get some sort of picture like this. So what we see here, you have a fixed pair of multisets, which first they're adversarial, so we know they're hard, especially for the smooth. But okay, it's a fixed pair of multisets, and you're increasing. You have some network you're applying and summing, right? And you increase the width. Okay, blue is ReLU, orange is smooth. Okay, and the red is the true W1 distance between the multisets. Okay, so and what you see is that so really ReLU, maybe initially cannot separate them well, or maybe up to numerical error it cannot separate at all. But at a certain point, it actually separates much better than the smooth. Okay, and this can be quantified using this sort of a relaxed notion of Bi-Lipschitzness, where you take you say that for fixed multisets S and S prime, you're taking the expectation over all parameters, and you want to look at something of this form. Okay, and in this context, ReLU can actually maybe be lower Lipschitz in some sense, or at least lower Holder. Okay, so we allow here an exponent of A, and we get results like this. So we can actually show that the ReLU, so the Holder exponent of ReLU is 3/2. So it's not lower Lipschitz, but it has a Holder exponent which maybe you can live with. And smooth functions always have a Holder exponent of at least n, where n is the maximal number of points in the multiset. Okay, and okay, so actually sort of the roles are reversed. Okay, so maybe that leaves us confused. But the main thing we're interested in is actually building something which is Lipschitz. Okay, time-wise, how am I doing? 24 minutes. Okay, I'll talk slower. Okay, so what I want to talk about is how to do something which is Bi-Lipschitz. Okay, and as I said in the beginning, so there was a spoiler, right? We're going to do this via sorting. Okay, so the starting point where things are really nice is when if you have a multiset and all elements are one-dimensional, they're real. Okay, so in that case, you can actually show that the mapping that takes these elements and sorts them is an isometry. It's exactly the Wasserstein distance, right? So that basically means that if you take two multisets, you sort them from small to large, and you look at the distance between the elements, that is the best you can do, right? If you permute these elements in some other way, the distance will always be larger, which is sort of intuitive. It's not, I don't think it's 100% maybe obvious, but it's true. Okay, so in one dimension, we're set, okay? We're good. Sort is an isometry, right? So Bi-Lipschitz with little c equals 1 equals capital C, that's perfect, okay? Also important for later is to note that sort is a continuous function, which is piecewise linear, admittingly with many, many different jumps. Okay, so maybe, in context, right? So if before we said that to be injective, if you take sum over ReLU, then because it's piecewise linear, then you can't be injective, right? So that's only because you're taking a piecewise linear function and summing. If you do something else, then you can be injective and Bi-Lipschitz, even with a continuous piecewise linear function. Okay? And now the question is how to generalize this, how to do multidimensional sorting. Okay? So if I have a set of n elements and they're in RD, they're not in R, right? So what is the analog of sorting? Or maybe there are many analogs, but what are we going to do? So the natural thing seems to be lexicographical sorting, right? So maybe we sort according to the first coordinate, and if there's a tie, so we sort according to the second coordinate, etc. But that is a very non-continuous function. And so it also will not be Lipschitz, and it won't be, so it will be injective, but it will not be Bi-Lipschitz or upper Lipschitz or anything. Okay, so that's not good. What we instead do is we basically take this multiset of n elements, and using this matrix A, we take many linear projections, and then we sort each linear projection on its own. Okay, so we have m different projections. We sort all of them. That gives us a map. Okay, so this map is continuous piecewise linear and homogeneous. And you can prove that if this m, again, is like twice the dimension plus 1, then this mapping will be injective for almost every A. Okay? Right, it's related to Slice-Wasserstein, right? Okay, in Slice-Wasserstein, so you're computing a distance, and you're taking expectation over all slices. So it's sort of like maybe like a sampling of Slice-Wasserstein. Okay? And you can prove, at least the way we prove this is via the finite witness theorem, although you can actually prove this also in other ways. But it does give you things. Never mind, I won't go into it, but just another example of how wonderful it is. Okay, and then we can couple. So first of all, you have injectivity using whatever tools of injectivity, and then you also have results that show that whenever this map is injective, it's Bi-Lipschitz. Okay, that's sort of like, right, you know that a linear function from Rn to Rn, if it's injective, it's always Bi-Lipschitz, right? It has a lower and upper, with the bounds are the operator norms of A and A minus 1. So there's sort of a result like that. It says if something is, if it's injective, it will automatically be Bi-Lipschitz. Again, to me, it's sort of there's a sort of more general tool you can use, which says that if you have any two homogeneous continuous piecewise linear semi-metrics with the same zeros, then they'll be Bi-Lipschitz equivalent. Okay, so maybe not, it's a little bit, maybe this is a mouthful right now, but what I'm trying to say is that we found this useful for other things, that you have, it's some sort of general thing that if you have two continuous piecewise linear metrics, they'll be Bi-Lipschitz equivalent. So it's something inherent in the continuous piecewise linearity. Okay, and yeah.
A quick question. The previous slide.
This one?
I didn't. Yeah. When you were using A.
Yeah.
So, what does A look like? I don't understand.
So.
Is there a distribution over A?
You pick at random.
Random? How random?
You optimize it, right?
What do I do in practice?
No,
in practice,
what is the measure over A?
So if I say, let's say, almost everywhere, so with respect to Lebesgue. So, or if you want a probability measure, so any probability measure that's absolutely continuous, you get the same guarantees, right? So I don't know, say normal. Okay. Yeah. And practice if you put this into an algorithm, so you can think of it as parameters you learn. And
Sure.
I mean, the best would be maybe the most homogeneous one gives you the best worst case guarantee, but maybe you don't even need that.
You mean like if you, let's say, sample them uniformly or something like that?
I mean, maybe you don't need that. So
No, I mean, yeah, in practice, it would be good to have the best Bi-Lipschitz bounds you have, and it seems like that's a good idea if you want to. But also, in the 2 dimensions, you can actually sort of choose things on like a grid, and if you do in multiple dimension anyway, you end up randomly generating, right? Like taking from the normal distribution or something, so.
Is M related? Again, oh, okay. So it's so there's some relationship to compressive sensing and stuff, right? Because you don't lose the signal if you do random projections.
Yeah, maybe. I mean, I can see the analogy. We don't use compressed sensing,
Okay.
but
you do the radon transform and then try to invert it numerically, then
Yeah, the compressive sensing does it with L1. Yeah.
It might be interesting actually to connect to this random projection, because there have been these theorems where you can actually, eliminate. You only have to look at, let's say, -1, 1, and like only a finite number of values for the matrix. So
okay.
kind of
I mean, yeah.
type of results.
Yeah, I mean, okay. So you mean like you don't need to look at continuous things, but only like. Yeah, I mean, there are related. I mean, so for example, you can actually prove this. Let's say if A is a what do you call it? A full spark. So you can prove something. If A is full spark, so it will be injective and stuff like that. So there are. I mean, there is also that. For the purpose. I mean, we are aware of this to a certain extent, and we do look in our compressed sensing book occasionally. Probably we could know more things, but yeah. Did we do this? Yes. Okay. Okay. Now, okay. So up till now, we were only talking about actually being Bi-Lipschitz without controlling the bounds at all. Okay. So we now have a result which is almost published, almost an archive, which says that you can bound this distortion by it's between n squared and square root of n, essentially. Okay. So, in somewhat more detail. So whatever you do, it will never be better than the square root of n. And if you take enough m to be large enough, more than n times d, then you can get something like this. We can prove that, like you draw these A normally, and with probability large enough, you get something like that. Okay, so that's, I guess, the last thing. There is a big, I don't know if big, maybe big, right? So there's some gap here, right? So we don't know if square root of n is actually, there's some construction you can get with square root of n, or maybe n squared is the best, and we don't know, or something in the middle, we don't know. So maybe you can steal that from us. Okay, so but we do see the distortion must grow with n, which is bad news. So n is the number of elements. On the other hand, the distortion does not grow with d at all, actually. So that's so this construction we have doesn't depend on d. So you can actually, so I don't know. I guess you can think if you have some setting where maybe you have a small amount of elements in the multiset, so even if it's high dimensional, maybe you can get a good embedding with this. Okay, let's say, I don't know, you have a graph and the degree is small, so that's sort of the number of elements. So you could get maybe a good maybe a provably good embedding in this thing. Okay. Okay. So now, if you remember, I said that sorting, right? All the sorting business actually is very dependent. You have to sort of assume, or it's most natural to assume that all the multisets are the same size. Unfortunately, that's not a very good assumption for graph neural networks applications, right? So, so we have two ways to deal with this. This is the ugly way. Is using padding. Okay, so somehow, right, you decide like what the maximal element that maybe you may ever see, and you pad it. So that works, but it's not beautiful. And this is the good way. So we use something called FSW embedding, which is very cool, but I don't have time to talk about, which is more natural. So it's like it's a very nice solution, I think, which I didn't think of actually doing this in whatever dimension. Okay, so this is from Taz's paper, and I mean I'm also written on it, but it's not my idea. Okay, and so what I want to end with is a few slides on sort of practical, right? So having said all this, so then what we'd like to show is that if you use sorting for graph neural network, graph neural networks, which usually use some or some other aggregation, we're going to put sorting in, our version of sorting, and then it's going to work wonderful. Okay, it's not 100% true, but to a certain extent, it's true. Okay, so the first way, to get this to actually be true, so the first thing we did is we did something empirical, synthetic, where we knew we were going to win, and it worked. So we took basically sort of an adversarial data set based on multisets where we know these things are very bad because we built it in that way. And there you see so it's like a binary classification task, and you sort of get something which is proportional to what we predict. So the sort is perfect. Forget about this adaptive thing. Let's make believe it doesn't exist. A ReLU, which is supposed to have better holder constants, performs better, and the smooth activations are worse. Okay, so that's a very, I wish everything was like that. Another thing you can do is, which makes sense also that should work better is the task of actually learning the Wasserstein distance, right? So if I know that I can get a certain approximation using this sorting-based thing, I can, I know it's Bi-Lipschitz, I can somehow bound the thing. So if I combine that with learning, so hopefully that maybe could be better than doing something like that with something sort of more like deep sets or sum-based, right? And that actually seems to be true. So we have here two methods, which this is sort of our method, and this is I would say that you can think of this as sort-based, which is much, significantly more accuracy than the deep sets-based thing. Sorry, I jumped. So that was good. Then we tried it on point cloud classification tasks, right? So model is 40. You have 40 different classes of shapes, which you can think of as multisets, right? You want to be invariant to the order. And we want to classify, and we just think of this as a multiset. We do a simple thing. We take, we compare FSW embedding, ours. This is our sort of the good alternative but think of it as sort-based with max pooling. And initially, the results are similar. But what we did see, which was nice, is that if you take, so say, the number of parameters people usually use is about here, and here you have sort of something which is, the two methods are similar, or maybe sometimes this is better or that is better. But if you reduce the number of parameters significantly, then the FSW embedding is much more robust to that. Okay, so you can actually get reasonable accuracy with much less parameters. The flip side of that is that also, for let's say at least for the same size of network, it's also slower. So somehow, there's some sort of trade-off here, which is maybe not 100% clear how to manage. But say, I don't know, if you want a small amount of parameters and you care less how long it's going to take, which I guess could happen, then maybe that's a good alternative. So I'm going to move from multisets to graphs, right? So up till now, we were basically talking about tasks on multisets. Now I want to talk about, you can take a graph neural network and you plug in this thing as the aggregation and readout. So we have two versions of this, the sort MPNN, which uses the what was it called? The padding, or FSWGNN, which uses the nicer version, but let's think of that as two sort-based things. You can actually prove that these things are Bi-Lipschitz with respect to metrics on graph space, so either TMD or doubly stochastic. Okay, so there you can prove that. You can also see that experimentally. So we have here some synthetic experiment where we generate a certain amount of graphs, and we look at the empirical distortion on this finite set. And you see, so for these two methods, which are sort-based, we see much better distortion. Although this is really super high, I guess, 10 to the 6th, but still much better. Okay, so again, yeah, this is the. Okay, we look at Okay, this is maybe a chemical property regression task. So here again, sometimes we win a little, sometimes we lose a little bit, but also we have this phenomena that as you decrease the number of parameters, so here as you go right, you're decreasing from 500K to 1K. So the performance of sort MPNN improves. And then last thing maybe that we saw as helpful is long-range graph learning. Okay, so we have this phenomena which was mentioned here that if you have a long-range task, so usually MPNNs don't perform very well. So there's over-squashing, over-smoothing. And what we've found is that these methods are sort of efficient and they can mitigate this issue. Okay, so at least it takes them much longer until they fail. So what you see here is like the problem radius. So there are various different problems where to get this to succeed, you need 8 message passing iterations. Otherwise, you're underreaching, and here are only 4, etc. Okay, and here these are our 2 methods: the turquoise and the yellow. So that works. I should say that there are many ways to mitigate over-squashing and over-smoothing, but this is we're doing this with the message passing as is. So you're not sort of adding a virtual node or something which you can think of sort of as cheating, because it's not really cheating, but you're shortening the path and solving the problem superficially. Okay, so that's it. Okay, so conclusion. Okay, so what we saw is that unlike standard multiset neural networks, sorting-based methods are both Bi-Lipschitz and injective. Okay, there's a sort of general concept of if you can build something which is smooth and injective, it probably will not be Bi-Lipschitz, but if it's continuous piecewise linear and injective, it will be. And we saw that in certain instances, sorting-based multiset functions can be helpful for learning. If you want to learn the distances themselves, or you want to learn with a small parameter budget or long-range tasks, stuff like that. And on the other hand, it can be slower. Okay. Future work, we can talk about the potential of sorting for other tasks. When we want to maybe take these methods and show that they can do well in other domains. One sec, something jumped. Okay, so the second bullet there was that you want to maybe try to find other methods which have better distortion than what we know, right? So we know that for multisets with n elements in RD, using our sort-based method, we can get distortion which is polynomial in square root of n, right? It's between square root of n and n squared. And what I just wanted to say about this is that this question of distortion also depends very much on what you're assuming. So for example, you can generalize the setup of multisets with n elements in RD to measures supported in n elements in RD, right? So you can think of multisets as like measures with uniform weights, and this is like a more general setting. It may not seem much more general, but we can actually prove that in this setting, there's no Bi-Lipschitz mapping. Okay, so on the other hand, there's some sort of different setting where you have measures, but supported only on a grid. Okay, so this is, it's a subset of this, and it's incomparable with that. And in this setting, it's actually, there's a pretty well-known paper that shows that you can get a distortion of log n, which is optimal up to a factor or something. So, yeah.
Can you remind, what the Bi-Lipschitz with respect to what?
The Wasserstein distance.
Between the Wasserstein distance.
Yeah.
So you are,
Okay, so if you make this assumption, you can get log n with a different method. If you make this assumption, we know how to get something which is between square root and n squared. Maybe you can do better. Maybe you need. So I'm saying, I think that there's a lot of there's possible room to improvement here, but maybe also depends on the assumptions. Maybe you need different assumptions to get better results.
what does it mean that doesn't exist the Bi-Lipschitz mapping?
So you can't map this to Rm and preserve the distance up to any.
From any metric space.
You have measures supported in n elements in RD. That's a metric space with the Wasserstein distance, and you can map it to R whatever 10 million, and be Bi-Lipschitz. OK. And that's it. Thanks.
So thank you for a really nice talk. So for the sort MPNN, you mentioned that it can be slower. And from my understanding, do you do the sort at every iteration of the message passing?
Yeah,
It's like an aggregation.
it's an aggregation.
It shows up at every link.
Yeah, that's your
So
aggregation.
is it possible that maybe in terms of thinking about how to speed it out, maybe after some rounds, you just don't need to store, or you don't need to store in all the dimensions?
Maybe. Yeah, I don't know.
Because
We didn't try.
then-
We didn't try that. Like
I see,
doing it
I
only
see.
part of the time.
Right.
There is a. Yeah.
Because with the sorting, you're adding the additional n log n sorting time for each of the iteration.
Yeah. Yeah. Maybe.
So when you had like a positive result about analytic functions, you said that's okay because in practice, nobody uses value, but then when differentiable functions didn't work, you actually introduced a value approach. So how do you minimize these two statements?
No, I didn't say that no one uses value. I think people usually do use
I'm just
value.
paraphrasing the-
No. What I was saying at a certain point, I said that activations are either ReLU or analytic. So I mean, whatever. I mean, not everything is either piecewise linear or analytic, right? You could have a function that's 6 times differentiable, but in practice, that's not very common. Yeah, I don't know. So I think it's true. There are sort of two contradictory results about ReLU and analytic. That's but mathematically they're true. But but at the end, the sorting is what we're going with. So it doesn't matter.
Other questions. So are there any results where you parameterize the number of bits that you're using? Instead of going full review or one finite, but just like some results, like what can you do if I say you can only use like I don't know, like precision?
Yeah. So I mentioned before. I didn't talk about it, but there was a result in like MPNNs using ReLU where you have like the features are discrete and you can count how many bits you really need, and there are lower bounds and upper bounds. I don't remember the name of the authors. I think the first author is called Amond or something like that. But yeah, there are such results. And yeah.
So I just wanted to remember well what can be a take-home message for the last graph you showed. Like you showed the one where you showed that the oversquashing is better by the. Or, I don't know if it's not the even here. Yeah, the next one. Yeah.
Yeah.
The other graph that was coming to.
Yeah, I don't know. Something gets stuck here. Okay, maybe I'm just not pressing hard enough. Yeah. Okay. Yeah.
So what would be what can I remember about the sorting being better? What would be the quality of sorting that makes this happen? Somehow less collapse in a sense?
Yeah, I mean, to me, it's right. It's like, I think the intuition why this should work is that it's better in preserving the information inside the multiset. So when you sum, even if it can be injective in theory, in practice, you're probably losing information. So that's how I understand it.
I mean, so one thing that this could be helpful maybe with like if you want to do this like this PC dimension bounds for message passings, right?
Mm-hmm.
There are few results. If I have several message passing, the set of function, how can I calculate the BC dimension? Because the composition of different function classes, you have very bad bounds.
Mm-hmm.
But so this hints that maybe sort activation can help you, or something like sort could help you for this theoretical kind of results. I don't know. I'm just saying.
Maybe, yeah.
In the wind.
Right. I mean, I was talking with Christopher about theoretically, the upper Lipschitz constant comes up a lot in generalization bounds, and the lower Lipschitz constant is not very popular. But I feel like it's a natural thing. But the question of what you need it for, like in terms of why it's good for learning or something, there's no I mean, even, forget about sort specifically, but why is this something you want? Then you can start looking for things. But so I don't have some statement saying the lower Lipschitz bound is good for whatever, controlling the VC dimension or anything. I don't know anything like that.
That's very interesting to me. I think it's really cool.
Thank you.
So I have a question more intuitively, like if X is a heavy-tailed with no second moment, then, and maybe the task doesn't care about the extreme values. So then what happens,
so X is like the multiset you're generating or
yeah,
something?
it's like from a heavy tail with no second moment, so you get some values that are really far away.
Okay.
But those outliers really don't matter. So but when you sort, they're going to be part of the sum. So,
Okay.
So do you have any intuition of what happens there?
No. I mean, what you're saying is maybe, it's not able to forget things that it should be able to forget?
Yeah.
Maybe, it's a good question. I don't know. I mean, certainly it doesn't always work so well, so, I mean.
But it would be interesting, just like maybe there are some conditions like this on the distribution of X, right? That under this distribution, then works better for this other distribution. And it also depends on the task, I guess.
Yeah, maybe. I don't know. Okay.
Okay, then let's thank the speaker again. Yeah.